Today I'm going to be explaining this important paper with the title Disentangled Graph Representation Based on Substructure of Graph Optimal Matching Kernel Convolutional Networks. This paper in 2025. Graphs offer an effective characterization of relational data in various domains, giving rise to graph representation learning and discover the underlying information for prediction. Graph neural networks have emerged as the state-of-the-art method, providing an end-to-end learning strategy for different tasks. Recently, disentangled graph representation learning have been proposed to enhance representation quality by decoupling the independent interpretable factors with graph data. However, existing methods still implicitly and coarsely characterize graph structures, limiting the analysis of structural patterns in graphs. Accurately capturing structural information of graphs has become the key to disentangled graph representation learning. This paper views the graph as a set of node-centric subgraphs, each serving as a structural factor to characterize specific information at various positions. So graph-oriented predictions are transformed into the problem of pattern recognition for structural factors. Inspired by CNN, this paper proposes graph optimal matching kernel convolutional network. To learn disentangled representations for individual factors, a novel graph optimal matching kernel is designed as a convolutional operator to calculate the similarity between each subgraph and several learned filters. Mathematically, GOMK maps each subgraph or graph filter into a point in Hilbert space, representing the entire graph by a set of points. The disentangled representation of a structural factor is equal to the projection of its subgraph into individual graph filters. Driven by the gradient of training loss, these graph filters will capture task-relevant structural patterns. Additionally, GOMK considers local correspondences between graphs in the similarity measurement, resolving the contradiction between differentiability and accuracy in existing graph kernels. The idea of coupled representation learning, you see a graph can be represented as a set of node-centric subgraphs. By mapping these subgraphs into a Hilbert space, these representations of individual structural factors and the entire graph can be obtained. So what is the definition of disentangled representation? Given the subgraphs and the training graph filters gamma, these gammas are training graph filters, the disentangled representation Z of node U is defined as the similarities between its subgraph and individual graph. Of course, if you remember the paper of Professor Braunstein in Oxford University, their representation is expectation over all of these, because you pick a mask from a distribution. So gamma in that article is from a distribution, it's drawn from a distribution of filters. But here it's just picking filter, there is no expectation. And the graph R convolution framework, that we need a base kernel in order to compare different substructures of graph G and different substructures of graph H. In order to compare G and H, we compare their substructures. So the framework is like this. First, we do subgraph extraction. We have subgraph centered and within k-hops, so individual nodes within k-hops. Then we have subgraph embedding, which we can do it with our convolution framework. Then we have subgraph matching. This is a little bit tricky. After converting a subgraph and a graph filter into a set of subtree embedding, a novel OMK is proposed to measure the similarity between sets. It establishes an optimal matching between subtrees across the two graphs. Finally, the similarity between the subgraph and the graph filter is measured by aggregating similarities between matched subtree pairs. So we decompose a subgraph or filter into T-level subtrees. And here you see the key mechanism in graph kernel. The R convolution framework calculates the graph similarity. And the label refinement here seeks to encode a tree by mapping all node labels into new label in an injective manner. So the framework of graph optimal matching kernel is like this. There are 3 steps. Step 1, we create k-hop subgraph. We have step 2, t-hop subtree encoding. Step 3, optimal matching. And the method of T-level subtree encoding is here. Firstly, the subgraph is decomposed into subtrees, routed at individual nodes, noting that the same node often appears multiple times. Here we have subtree matching based on greedy algorithm. Firstly, the similarity between any 2 subtrees across subgraph and the filter is calculated. The darker the color of square, the higher similarity. Secondly, the subtrees within subgraphs sequentially select the most similar counterpart in the filter, as is shown in the second and third rows. Once a subtree has been selected, it will no longer participate in subsequent matches. Thirdly, the similarity between the subgraph and the filter is measured by the sum of paired subtrees, similarities indicated by the check marks. And they use the following TSE, which is divided into 3 steps. TSE, it means T subtree embedding. So first we have level embedding, then we have subtree embedding, then we have subgraph embedding. Level embedding, the features of nodes are aggregated. The subtree embedding, the layers embedding are combined. And subgraph embedding is at the level of subgraph. Then they do here the element matching, the matching that maximizes the sum of similarities between element pairs. We call it optimal matching. But the solution is combinatorial optimization. However, current machine learning platforms lack parallel optimization for this algorithm, so in this paper we propose a greedy algorithm as an alternative solution. Given a subgraph and a filter, each represented by a collection of subtrees, the algorithm sequentially seeks the optimal matching subtree for all subtrees. So you see here, given the embedding of 2 sets, their similarity can be measured by the histogram intersection kernel. So we have node-centric subgraph, we have level embedding for subgraph, and then subgraph matching. Finally, we have this disentangled representation ZU, which is a set of similarities. You see the variation of graph filter at different epochs. As we increase the epochs, so for example at the epoch 280, we have a well-defined filter. But at early stages, it is not well established. Then we have framework of isomorphic graph learning here. That we have ground truth, then we have graph filter, and then we have this isomorphic loss. And this is the results of isomorphic graph learning. This is illustration of frequent graph pattern mining, because it can discover different filters, very different filters. For example, what is the frequency that this filter appears is just 6%. But this filter is more often happens, it is 30% of the time you have to deal with this filter. You see this in different subgraphs of the graph. And the method they use, like k-means, we define the training loss by maximizing similarity between each subgraph and the corresponding frequent subgraph. And this is illustration of model interpretability. So they did experiments on these benchmarks on enzyme protein, which are very good for graph classification. For example, they compare graph isomorphism network, or SAG pool, or top K pool. These are hierarchical graph pooling. SAG pool, top K, with the GUM KCN. Even a graph isomorphism network is very similar. The results is very similar. 72, 73. So it's almost similar.